Today's class is on organic reaction mechanism, types of bond fission, types of reagents, and the reaction intermediates, as well as types of reactions.
Today's class is on organic reaction mechanism. First, we have to discuss about the R&S nomenclature. In our previous video, we have already discussed about this, how we can assign either R or S to a particular chiral compound or optically active compound. See this, here the compound is, this is the chiral center carbon, Cl, H, this is the CH3, this is the OH. So actually, this is a two carbon system, 1-chloroethanol. Now, this is the structure where Cl and H, these two groups are on the plane. See this direct straight line, so these group represents the are on the plane. CH3 group on the back side, below the plane. OH above the plane. Now, if we want to convert these three-dimensional structure into Fischer projection form, now see that Cl and H on the horizontal line, CH3 and OH on the vertical line, where CH3 goes towards the up and OH goes towards the down. How it comes? See this, Cl and H. Left thumb express the Cl and H denotes by the directional finger. Now, below this, see this, below the plane, see this CH3 group, and towards me actually, this is my right thumb, it expresses or it denotes the OH group. So if we tilt it 90 degree, then this represents the horizontal bond, that means Cl and H, this represents the horizontal bond, and CH3, which was below the plane, goes towards the CH3 group, goes towards the up, and OH at the down, both are below the plane, and that's why to the vertical bond. CH3 and OH are on the vertical bond. So see that Cl and H are on the horizontal, CH3 and OH are on the vertical. Now, if we assign them as A, B, C, D, see that maximum mass containing group is Cl 35.5. This is the maximum mass containing group A, denoted by A. Oxygen having the mass 16 and carbon 12, so B will be oxygen, that means OH group. C will be CH3, that means 12. Now D, hydrogen becomes D. If we rotate our finger from A to B to C, A to B to C, then see that it is anti-clockwise. If it is anti-clockwise, then it is assigned as S. But after assigning R or S, whatever may be, we have to find out the position of D. Here D is on the horizontal line. As D is on a horizontal line, hence it is just invert of these. Instead of S, we have to write this is R. So the nomenclature of this configuration is R. If D is on the vertical line, so if it is anti-clockwise, then it becomes S. If it is clockwise, then it becomes R. But if it is on the horizontal line, which comes in case of anti-clockwise, which comes S, converts to R. If it becomes clockwise as R, then it converts to S. See this in our next example. See that COH and OH. So COH and OH on the horizontal line. See this COH and OH on the horizontal line, and CH3 and NH2. See that NH2 group is below the plane and CH3 above the plane. So if we tilt this, then NH2 and CH3 go to the vertical line, NH3 to the top and CH3 to the bottom. See this on the vertical line, NH2 to the top and CH3 to the bottom. Then we have to assign A to B to C. First A, that means oxygen, mass number 16. Then B, nitrogen, mass number 14. Then C, carbon, mass number 12. This also D, carbon, mass number 12. But see that with this carbon, the second option is oxygen, which has mass number 16. But here second option is hydrogen, which has mass number 1. That's why according to the priority rule, COH will be C, CH3 will be D. So if we rotate our finger from A to B to C, then OH to NH2 to C, that is anti-clockwise. As it is anti-clockwise, it becomes S. But here the D, position of D is on the vertical line, so it remains same. That means as D is on the vertical line, if it comes S, then it becomes S. If it comes R, then it becomes R. That's why it is ACE. The configuration of this compound is ACE. Now, these R and S nomenclature we have already explained by using two different examples. One becomes R and other becomes ACE. Now we have to assign 1 degree, 2 degree, 3 degree and 4 degree carbon atoms. How it comes? See that the compound 1 degree, 2 degree, 3 degree and 4 degree carbon atoms. So this is the 2,2,3 trimethyl pentane. 2,2,3 trimethyl pentane. Now if we assign these as this is the 1 degree. How it comes 1 degree? Because we have to see with how many carbon atoms it is directly attached. If maximum 1 carbon atom, it is attached with maximum 1 carbon atoms. Maximum 1 carbon atom attached with. Then it is 1 degree. If it is attached with 2 carbon atoms, it is 2 degree. Attached with 3 carbon atoms, it is 3 degree. Attached with 4 carbon atoms, it is 4 degree. So see this carbon is attached maximum with 1 carbon directly. Directly attached to it. Right now we can see that directly attached to it. So it is 1 degree. See this carbon attached with 4 different carbon atoms, and that's why it is 4 degree. It becomes 1 degree. But here this carbon is attached with 3 carbon atoms directly. That's why it is 3 degree. This carbon attached with 2 carbon atoms with it. That's why it is 2 degree and it becomes 1 degree. So if we want to assign a particular carbon atom by using degree, we have to observe how many carbon atoms are directly attached with this particular carbon atom. If 1 carbon maximum attached with this, that is 1 degree. 2 carbon atoms, not with maximum, but 2 carbon atoms directly attached with this, the given carbon is called a 2 degree. 3 carbon atoms directly attached, 3 degree. 4 carbon atoms directly attached, that is 4 degree. Now we want to see that alpha and beta carbon or alpha and beta. So see this is the double bonded position. This is the alkene system. If we want with respect to this alkene, which one is alpha? Directly attached carbon is alpha, and alpha attached with the carbon or oxygen or nitrogen, whatever may be attached with that atom, is called the beta atom. So here alpha beta unsaturation occurs. That may be like this. Alpha beta unsaturation occurs. This is also alpha, this is also beta. If we mark this part alkene as the main part, then it is alpha, this is beta. So directly attached carbon is called the alpha carbon, and the carbon which is directly attached with the alpha carbon is called the beta carbon. Now these are the defined forms of the alpha and beta carbon atoms. Now we are discussing about the first bond fission. What is bond fission? This is the breaking of bond. So in a particular chemical reaction, the older bond breaks and newer bond forms. This is the process. Now breaking of bond may take place in two types, in two ways actually. Suppose C single bond C or C single bond X, whatever may be. X may be a reagent, a reactant type pieces like nucleophile, or whatever may be an electrophile, may be a living group, whatever may be. So first type is homolytic bond fission. Homolytic means equal distribution during the we know that this is a covalent bond, and covalent bond means sharing pair of electrons is present there. Therefore, in case of homolytic bond fission, the equal distribution of the electron takes place. One electron goes toward this carbon atom and one electron goes toward this carbon atom. Now here also one electron goes toward this carbon atom or one electron goes toward the X atom. So it generates a dot, that means it is called the free radical. This is called the free radical. Now free radical. But there also may take place heterolytic bond fission. Heterolytic means unequal bond fission. So if or whenever, suppose X is more electronegative than that of carbon, so during the bond fission X pulls total electron density towards it and hence generates a C plus, which is called carbocation, or it may occurs like carbon is more electronegative than that of X, then total electron density will be shifted towards the carbon, and hence it generates C minus, which is called the carb anion. Carb anion. Now these three are called the reaction intermediates. Reaction intermediate. One is the carbon free radical, second is the carbocation, and third is the carb anion. These three are called the reaction intermediate. Now carbon free radical, we know that this is sp2 hybridized, this is planar, this is highly reactive species, highly reactive species. But in case of heterolytic bond fission, either it generates carbocation or carbon ion. We know that carbocation is also sp2 because it contains only 3 bonds. One orbital is totally empty, totally remains vacant, and hence it is sp2 hybridized. It is also planar, but it may get stabilized, Also, carbon ion. Carbon ion is sp3 hybridized because it contains a pair of electrons at a particular orbital, like this carbon. These three are the bonded part, like A, B, X, etc. and so on. But these orbital contains 2 electrons, which is actually produces this negative charge, which produced the negative charge over the carbon atom. That's why it is pyramidal in shape, not the tetrahedral, but it is pyramidal in shape, and it also may get stabilized. Now how it generates? Actually, first, during the heterolytic bond fission, we know that in maximum cases heterolytic bond fission occurs, but only in case of these 5 conditions: H, E, L, P, R. Rather, we can pronounce helper. So only in case of these 5 conditions the free radical is formed. That means this free radical is obtained. Which are these 5 cases? Number 1, heat. In presence of heat which is greater than equals to 500 degree centigrade temperature. So if it generates more than 500 degree centigrade temperature, then the intermediate must be a free radical. Electricity. E denotes the electricity. If the electricity passes through a particular carbon-carbon single bond system, then the bond during the bond fission free radical occurs. L is the light, that means sunlight. L is the light, which is nothing but the sunlight. So in presence of sunlight, the reaction occurs must produce the free radical. Like H nu, it is denoted by sunlight is denoted by the H nu. It must produce the free radical. P, this is the peroxide. In presence of peroxide, the intermediate forms is also the free radical. In presence of peroxide, hydrogen peroxide, later we can see that in case of anti-Markovnikov reaction, peroxide effect, in presence of peroxide it produces a free radical, and through the stabilization of the free radical the reaction proceeds in a particular mechanism. And R, that is, and R is the radical, that means it is also a free radical. In presence of a free radical, this is also a free radical, in presence of a free radical it generates the radical. So these 5 are the conditions in presence of which only free radical generates at the intermediate. Types of reagents. Now we are discussing about the types of reagents. See this. Suppose this is a compound CX. This is the reactant, and we have to use a reagent here, and that reagent may be a positive charge species or negative charge species. So on the basis of their positive or negative charge, these are classified into 2 types. Number 1 is the electrophiles. See this term, electrophiles. That means electron plus philicity. Philicity means loving or attracting tendency. Loving or attracting tendency. Philicity. Now this is called the electrophile. Which are called electrophile? Which attracts the electron. That means they themselves are the electron deficient species. They themselves are the electron deficient species. Now, electron deficient species are again classified into two types. Number one, neutral but also electron deficient, like BF3, AlCl3. These are the electron deficient species. How they become the electron deficient? Because we know that boron, aluminium, they are the elements of the group 13. So last cell contains 3 electrons. As they form the bond with 3 fluorine or 3 chlorine atoms, so through the sharing pair of electron, they occupy 6 electrons in their valence shell, less than octet. That's why these are the electron deficient species. So neutral electron deficient species are also called the electrophile. And number 2, the positive charged species. Positive charged species, that means the cation. Like all cations are electrophiles, like H plus, Na plus, all metal ions, etc. So all these are called the electrophiles, and it is denoted, these are denoted actually by E plus. Electrophiles are denoted by the E plus. Now second point is the nucleophile. Nucleophile, which are called the nucleophiles. These are the nucleus felicity, nucleus felicity. Now nucleus means positive charge species, felicity means loving or attracting tendency. So it attracts the positive part towards it. Now that's why these are called the electron rich center. Which are called the electron rich center? These are also two types. Neutral electron rich center, that means they contain lone pair over it. Example, ammonia, which contains a lone pair over the nitrogen. Water, which contains 2 lone pairs over the oxygen atoms. As well as negative charge species, which are called the anions. All anions are generally nucleophiles, like Cl minus, Br minus, I minus, OH minus, etc. and so on, etc. and so on. So these are called the nucleophiles. Now we are discussing about the types of various reactions, organic reactions. There are 4 types of organic reactions. Number 1, substitution. Number 2, elimination. Number 3, addition. And number 4 is rearrangement. So out of these 4 types, rearrangement occurs only in case of maximum 5% reaction. So maximum reactions are of either of these 3 types: substitution, elimination and addition. See this, in case of substitution reaction, when single bond gets substituted to form a sigma bond, that means sigma bond breaks to form new sigma bond. This type of reaction is called the substitution reaction. Example, this is a example, CCl, that means CH3Cl. When it is treated with aqueous KOH, the product is CH3OH. See this, the Cl group is substituted by the OH group. So sigma bond dissociates or breaks to form a new sigma bond. CCl sigma bond dissociates to form COH sigma bond here. This is a part of substitution, a case of substitution reaction. Second part is the elimination reaction. Here C single bond X, at least 2 carbon atoms are needed to form C double bond C. That means the main characteristic is that sigma bonds dissociate to form pi bond, new pi bond, to form a new pi bond. Example is this is the point A, B is the example. Example is CCOH. In presence of concentrated H2SO4 at 170 degree centigrade. Concentrated H2SO4 at 170 degree centigrade, it forms a double bond through dehydration, through the removal of water. So sigma bond dissociates to form a pi bond. This is the type elimination reaction. Number 3, this is the addition reaction. See the form addition reaction. Addition reaction. This is the double bonded system forms a single bond. So here pi bond dissociates. Pi bond dissociates to form sigma bonds. Sigma bonds. This is the characteristics. Example is CH2 double bond CH2 reacts with bromine in CCl4. Product will be CH2Br, single bond CH2Br. This is the example of addition reaction. But the rearrangement type reaction is very few. The example is like this. One is this ammonium cyanate NH4CNO. This on heating produces NH2CO. This is the urea. So this is the rearrangement type reactions. Now among these three types, first three types, which are the main: substitution, elimination and additions. Among these three types of reactions, substitutions are classified again SN1, SN2. These two are actually first, and the third is SNI, inversion. So SN1, substitution nucleophilic unimolecular, substitution nucleophilic bimolecular, substitution nucleophilic with inversion. And second, it occurs in very few cases. And the next part is substitution electrophilic. Generally it occurs as electrophilic aromatic substitution reactions. Electrophilic aromatic substitutions. In case of elimination, these are the types: E1, elimination unimolecular; E2, elimination bimolecular; and E1CB, elimination unimolecular with respect to conjugate base through the formation of anion. Now addition reactions are again classified into different types. Mainly addition reaction is of different types. Mainly is Markovnikov addition and anti-Markovnikov addition. Later we can see the different other forms of such addition type reactions in our next classes. So these are the different types of organic reactions occur.